Do you know anything about LiDAR? What do you think? What do you know about LiDAR? Any idea? Yes.
Active, so you measure the return.
So you have something active, you're shining a beam. Can you get me one second? Yeah. The first one, sorry. So okay, so you have an active beam. Yeah. What else? So you know about that. What else do you know? So you're measuring the time it takes the reflected beam to come to you. So it's time image. So it's one way to get elevation or topography. In ocean, they use them often for the theater. On shallow theater, I think that about that. Anything else? Yes. Very limited elevation. You know why? So it has to do with the technology to make the laser. So lasers are made in these. Lasers are very, very narrow spectrum. Not. And so to make it, you have to make it. I mean, they're made with. They're very intense, and they're made with very accurate crystals, and the wavelength you get has to do with the properties of the material. Trying to make that. And yeah. Anything more? No. Anything else about the LiDAR? Yes.
Do you measure it? How it?
So you measure return. So with the answer that you shine light, and then you measure. You know when the light came out. The laser went out into your system, and then you measure it. Through the principle of the measure. Now then comes what it is. Obviously, attenuation is what
Actually, a profile information to use it.
yeah, so you can, if you range gauge what's coming back, you know that the signal that comes first came from close by, second came from further away, further away, further away. So by that, you know. And if you assume the single scattering, each one of them came from a different depth in the material that you're requiring. Anything else? Great. So the reason this is really important for me and for a bunch of other people is because we feel that there should be an ocean like that. And I hope that by the end of the class you feel the same. And we want one to play with, people to study with the ocean. So this is my one of my motivation beyond the others. So some of the limitations we have with passive ocean color is that we told you from the beginning about 90%, we know 90% of the signal it comes from the atmosphere. And the ocean signal is only 90% of it is one optical band. You don't get information about the vertical distribution in the ocean. It obviously it doesn't separate absorption and scattering. Both of them versus. And then if you're doing globally, aerosol clouds and solar angle are issues that affect this. And you don't get any information about at night. At night means also polar night, as well as at night during the night. But this is a passive measurement because here, what's the source of light? Sun. That's our source of light. With a LiDAR, which means light detection and ranging, which is similar to things like radar. or what are the other R's we have here? Sonar. So all of them are ranging. Ranging means that the time variable. The signal is a known source. So you know what the source is and how intense it is. It's always the same during geometry, or you can set it during geometry, whatever it is you want to know. Minimal atmospheric correction issues. Because you're looking, because you know the atmosphere from the first signal that you get, just above the water, that gives you what the atmospheric path is, and then that's known for anything from each of the water. It can penetrate quite deep into the photoplayer, about the 4/c, kind of back of the envelope penetration, 4/v. You can therefore resolve vertical structure if you resolve in time well enough the detection. It can directly separate absorption and scattering, and we'll go how it's done, but that requires more information than standard lidars. Can retrieve aerosol, can retrieve when there are thin aerosol in clouds, you still get a signal, and you can measure during the day and during the night. And actually, by having the two, you can get information about processes at night that are different than processes in the day. By contrasting them. Oh, sorry. This is, and most of this talk came from Mike Bernfeld, who has been a big proponent of this technology. So I'll go through a little bit, and we went through how it works, some field work, what's available today in space, and then some science related to that, and then what it is we hope to see in the future. So this is your telescope. There's a laser pulse that you have your laser that's sent down. You have an aerosol layer before. It scatters photons, both from that and from the ocean, but each come at a different time to your sensor. So your detector first sense what's close to it, so a layer of mostly molecules, aerosol and clouds. There's more as you get close to the ocean, and then you get a very strong return from the ocean surface. And then as things decay below, you're getting the backscatter from water, and more of them are attenuated from deeper and deeper depth. And so you measure detected power as function of time, which is as function of depth. Typically, the laser is a 1064 nanometer fundamental wavelength, and then you can get harmonics of that. So you get the 532, which is green, and you can get also the 355, which is a UV one. The source is polarized, and you can look at the polarized emission. You can have a cross-polarized scattering channel and a co-polarized scattering channel. And those really help, can help a lot in cleaning the signal coming back. There's a you can detect fluorescence with them. So you can, for example, excite CDOM fluorescence with the 355. You can excite some phytoplankton with the 532. It has, so then you can do a whole bunch of different filtering. We're not going to get to that, but the vertical sampling is the most important thing. So the sampling rate of the detector in sensitivity allows you to get, that determines the depth range you can get in the water. Exactly. So co means in the same polarization plane as the LiDAR, as the laser that you shine, and cross is 90 degrees. It's the two linear ones. What? No, it does not measure all the others. If you did, you can get fluorescence. So sometimes it does in other ways. The detectors in the and you have to block the very strong, relatively strong signal of the one.
It's a really nice program. Coastal water to profiles of coastal fluorescence. Not very deep, because of course, flat water is shining way out. It's really shallow water.
So this is an example of the kind of data you get. You get a curtain of distribution where here is the aerosol backscatter, and we'll get in a second to how you get backscatter from it. This is in the atmosphere. This is a flight of a system that we're going to talk about from Langley. They flew a whole bunch of missions with, and you can see here smoke and then you can see what they're getting in the water, and you can see that the depth changes depending on how much attenuated material there's in the water. The more material there is, less you can resolve it. And you can see that there are gradients that are able to resolve. And here, this is the attenuation. So there's two numbers that they get out. They get an attenuation that's typically K6. It's the attenuation of the system, but it turns out it's very close to the diffuse attenuation coefficient for sunlight. And they get a backscatter. And this is the way by which one could separate dB from absorption, because these are two different parameters. There's the attenuation along the path of the beam, and then there's the stuff that back it to the, and we'll talk about how we do it. It's not at all.
Well, is it showing that it's measuring incorrect depth because of the amount of attenuation?
Yeah, so the point here, so this is this line. It's the line here, but in the water. But this is not the depth of the water. It's where you don't get enough return. It's where the return is too weak. Good question. And this is in the green, 532. So the harmonic. So this is the plane that they use, by the way. And we used it in a field campaign called Names. We had 4 cruisers. On the 4th one, they could not fly it because it was too dangerous to fly. The NASA didn't let them fly it anymore. It's an old. So some LiDAR have been in our community for very long. People looked at chlorophyll fluorescence starting in the 70s. A lot of work by Nelson Hogg in the 80s. Flying, looking at chlorophyll, phycoerythrin fluorescence, looking at backscattering attenuation and layers. Here, our paper where we looked at CDOM fluorescence. There's a whole bunch. So we've known of the utility of this technology for very long. Then there's somebody else called Jim Churnside, who's still very active. He's been looking at fish schools, doing sardine surveys he works for NOAA, and later on he got into biooptics more, but initially it was all about fish counting. So you can do large organisms with it. It can detect, fish, and some vertical distribution. This is from some of his papers. And there's also sheep LiDAR profiling. So people have built them and strapped them to a sheep, put it in the front, and that's like an inline system. You continuously, wherever the boat goes, you get a profile of what's in there. And somebody who's very active in it now is Dick Zimmerman from ODU. This is his student paper, where what he finds is that he can link nicely, and this is done in a cruise in the Gulf of Maine, the backscattering ratio to the linear depolarization ratio, so the ratio of co and cross polarite. From those, he gets a relationship that can say something about the composition of the particle. And in particular, in this case, they were looking at for colitophore. They went on one of Von Vulture's group. So, this is different promises of this technique and this technology. And it's now much, much less expensive than it used to do to build those. I mean, this is an in-house built at ODU. Now, the question is, can we do it from space? Going to space, there were some proof of concept doing it from the shuttle in '94, 3 wavelength, and they were able to do some maneuver over Lake Superior and Gulf of California and see a signal coming from below the surface. And then Calliope, which has nothing to do with the ocean. It's a sensor. It's on Calypso. It's a sensor that is a partnership between the French and NASA. NASA is the French space agency. Launched in 2006 and is still active. Extremely useful sensor. Not designed for ocean application. The depth beam in the ocean is 23 meters. So you don't get any profiling capability. 2 wavelengths, the green and the fundamental. You have 3 channels, the co and the cross polarizing 532 and the returning at infrared. It's a big telescope of 1 meter each size. The footprint is 100 meters. I told you the vertical resolution. It's polar orbiting, and every 16 days you get a repeat cycle. Measures in both day and night. So think about it. I mean, people for quite a long time said, you know, this is too much. It takes too much power to do from space. It's an active sensor. Since 2006, so this has been in space 15 years, and it's still going. So totally within our something we can do. And this is the guy who helped make use of the Easy Langley, take use of the in-water signal until he came and did his magic. And we still are not sure about all the details in the magic. It's the signal in the ocean, we couldn't get it. Ocean Color meeting in 2007, Mike and he met and started discussing how you could get, how you could get and validate the signal from the ocean. And there's 2 papers that came out in 2000 and this is in 2013, where they compared it to other satellites and found that the signal that Young has been extracting actually fits really well with MODIS and other sensors. So then came another, so this is from that series of paper, and suddenly you get data from a LiDAR in places where Ocean Color cannot work, like polar night. And they extracted, they looked at the distribution of backscattering, and what you're finding is it's quite different if you use MODIS data with QAA, that's this blue, then a different GIOP-like algorithm, GSM, and Calliope in terms of global distribution of backscattering. If you take it all the frequency of distribution. So, but the values are relatively reasonable. You know, they're overlapping. So it's not like one is orders of magnitude off the other. So there's something in the signal, and Calliope points out that maybe there's some biases if you use one versus the other. But it's completely independent. The beauty of this is it's another satellite using a completely different technology. So when you're looking at the concept of closure, which we've been beating into your head, this is really a way to do closure with, yes.
These are like carbon. Particulate or
No, this is particulates inverted from backscatter. So they really, all these, both are, these QAA and GSM give you backscattering, and then you use some other model, some proxy model to go into POC. Yeah. Yes. No, it has to do with the fact that the signal that comes from the top of the ocean, I can use that to tell me how much is attenuating because of the and then use the same attenuation on everything coming from inside the ocean. So I know the atmosphere by the signal that comes earlier, it tells me how much attenuation to cover the atmosphere. you know exactly when the crossing interface. The interface is such a strong reflector that you know. So the signal just above it tell you how much the atmosphere is taking out. And if you assume that it's going to take out just as much from whatever goes into the ocean, then everything else is ocean.
Anyone think LiDAR color?
Yeah. So that was, I mean, people want it. So initially in the discussion with FACE, there was the possibility of maybe having the LiDAR data. We didn't have. And so this is why there's another mission coming up that's in the cable survey. It's called now, it used to be called ACCP, now it's called AOP, which is one for aerosol and clouds and we're very strongly pushing them to improve our community as part of their science and to think about the sensor not just for the atmosphere, but think about what we because yes, it could be what?
What's their goal in AOP?
No, it's not.
I know the choice.
Yeah. I don't remember the acronym, but yeah, it's been very, very hard to get them. They feel that we've stole face from them because face initiative that ANC was aerosol and cloud. And that, you know, even though half of our science is atmosphere control. And so there's a, yeah. But the sense is if by small amount of investment, if we can make a sensor much more useful for other communities and allow for science in the interface, because one of the beauty of these, for me, one of the beauties of these sections that I just showed you, come on, of these sections, is that you can study in the same place what clouds do to the ocean. So is the smoke fertilizing the ocean? You know, all these processes, is the ocean producing cloud condensation nuclei that are making clouds. So this is a great way to study processes in the interface that are benefiting both communities. And so the more we have sensors that we have experts from both communities coming to the table, the more we can study these processes.
Yeah, the aerosol backscatter would really solve the aerosol issues that we have in
It will help a lot. It will help a lot.
And allow you to get spatial variability of the sites that right now there's some that's run out, you don't suppose, things that are in the atmosphere.
And what depth they're in. I mean, the nice thing with the LiDAR, and this is currently, is it tells you what depth the aerosol are. And they don't act the same way if they're higher up or lower down in terms of the atmospheric flow. So depending on where you are makes a difference. And currently we don't resolve the height well of these aerosol layers. So this is some data that, this is the little bit of backscattering data that's available in CBAS at the time. So this is like 2 years ago. We're helping a lot. Fill it up. We're not doing that. So LiDAR really shines where there's no light and a time where there's no light, both in both poles. And this is the beauty in December in the Arctic or in June in the Antarctic, you can get data from the LiDAR. These are all good retrieval from the LiDAR. It gives you indication about backscattering from which phytoplankton carbon is inverted. This is a paper, and then you can do an annual cycle in the properties from both, and you can see how well they match. And it's quite large beams in order to get them to match, but you can see how well they follow each other. And then from these, you can calculate a whole variety of things. So these are the times where you would not get MODIS. All these hatched ones is when there is no MODIS data, where the LiDAR gives you the fills in the blank. So we use them in a variety of studies to look at what's happening in the annual cycle. This is rate of change of biomass. So what we call accumulation rate is if I look today versus yesterday, do the difference, divide by time, I can get a biomass rate of change from those. And then from these, I can also look and I can also get rates of division rates, not from these. This is from other primary productivity models, but you can see when the bloom terminates, when you stop accumulating really, and that's when the division rate is actually maximal. The bloom starts when change is still very, very small, and you have the initial rise in biomass. And then after here, when you still have high growth rate, but they're decreasing, you're starting to see a net loss of biomass. And we've been, with Mike, we've been analyzing this for a long time in a whole bunch of places in the world. But what we found that's really astounding is if you look at the division rate of change. So now they're dividing. So you have your primary productivity. You divide by biomass, you get growth rate. We now look at how the change in growth rate goes. It goes very, very closely with the biomass rate of change. And these are these are different units. I'm just warning you. This is in day to the -2. The other one is in day to the -1. And it turns out that you can explain this pattern by a simple phase shift between loss processes and growth processes. If you simply say that the loss process is equal to growth 2 days ago, but today my loss rate is just equal my growth rate a day ago, 2 days ago, you're going to get exactly this type of behavior. Which is astounding. So the temporal lag between predator or loss processes to phytoplankton division rate can explain the annual cycle that you're observing in these properties. That's a bit of science. But something else that's really important with LiDAR, and we discussed, is disclosure with radiology. This is looking at backscattering comparison, as I showed you before with POC, but in 3 different regions of the world. You have Calliope in blue, you have MODIS in red, one of the inversions. This one, in this case, it's the GIOP one, but they're all similarly, they all track each other relatively well. And then the Argo float array that we now have Argo a lot in the Southern Ocean and in a few other places. And that measures backscattering at 700. It's not exactly the wavelength, so we propagate it into, but if you look at annual cycle, the annual cycles are very different. You can see here, for example, Calliope tells you there's not much of an annual cycle, while MODIS tells you, yes, there is an annual cycle of about 20% in magnitude. If you go to other places, you can see how bad the closure is. In some region, it's better. Northern region, higher latitude, they track each other better. But particularly in places of low biomass, they seem to diverge in very serious ways. And this tells us that we have a major problem. And we're trying to track it now. So this is the paper I told you many times about, this Spisa et al. It's in your folder, but that points out to the fact that we have this large seasonal bias. And we tracked it also then we went with this and we went to MOBI, and you find that in MOBI, you still have that bias relative to, so you cannot say, oh, it's the Argo floats that don't detect it right. Or you cannot say Calliope is not extremely well calibrated, et cetera, et cetera. There's an issue. There is an issue. And without the data from Calliope, the global data, we would not have been able to say, and there's this problem in passive remote sensing, because all passive remote sensing have the same bias. Whether you do it on an Olchi, whether you do it with VIIRS, it's not a MODIS issue. It's a passive versus, it's a passive issue, which is likely one of the, having to do with the atmospheric correction. And Kelsey is doing more stuff. I'll show you some of it in a second. But Mike went further, and he used the difference in day and night as a proxy, as something that tells him beyond what happened to phytoplankton in terms of daily cycle that we know about, that the difference from the daily cycle from what you expect is a signal most likely from migrating organisms into the upper ocean, and as a way to constrain migration. I'm not going to get into it, but just something else that you could do with active that you cannot do with passive. So in short, Calliope allowed us to show that LiDAR can work for the ocean. Before it, we could not say we want a LiDAR, as did CGCS for passive. It's an independent assessment of plankton stock to constrain onshore, and therefore, as you said, will help constrain ocean color algorithm because it's an independent. If you have an independent way of getting DV, then you can use the active, for example, to better constrain A. Polar observation addressed a major challenge for ocean color sensor, which is the night, and yeah, the constraint on data cycle. There is another LiDAR. It's called ISAT-2. And ISAT-2 is a photon counter. It's mostly used to do ice thickness. That's the reason why they designed it. But it also provides measurements in the water, and you can get vertical profile, amazing vertical profile in the ocean. I mean, it's very rare that it passes exactly where you want. This is the same. This is the equation I did not introduce, but this is the Lidar equation. So the Lidar depends on an attenuation and a backscattering. It's going to come back afterwards. This is the attenuation, twice the attenuation back and forth of the signal. And it's, if you're able to separate these two or relate these two, this is what we're doing in Calliope currently. We're relating these two. They're not independent. So you have to come with some bioptical assumption. Then you can solve for one. What? S is the signal strength that you're measuring. So the LiDAR measures it in time, and then this is translated into depth between two. We're going to get to this equation again, but you can it's counting photon coming and telling you exactly where they come from. Kelsey is on the science team for these sensors. So they have in their science team, they have geologists, they have atmospheric scientists, they have oceanographers, and they work really nicely together, including in producing software for all of you to download the data and use it for your studies. The sampling geometry, which I don't fully understand, the tracks are 90 meters wide. There's a weak and strong beam. Again, I don't know exactly why they're doing that. So the three of these beams flowing. And there's more in this paper by Marcus, which is probably the science lead for that mission. They've already been, there's already a paper published showing ocean blooms along the track from Lou et al. 2020. Kelsey herself just as a paper in Reviewing GRL, looking at relationship between backscattering and in leads close to ice with this sensor. And our physical oceanographer, they use it for sea surface height, particularly Andy Thompson, that's looking at how, if you know the satellite exact position, you can use it as an altimeter, just as we talked about before. Anyway, so the data is not limited to the pole, available everywhere. This is where you're going to go to get the data, and there's open access software to process data. So they're trying to be, they wrote a whole library in Python. They're trying to be as reaching out and as available as can be in terms of data. So the whole community, they want to see many, many more people use this data. So this is another LiDAR. And again, 532, it's available. So the problem of the LiDAR is, as I just mentioned, the fact that you're trying to get two parameters from one number, the backscattering and the attenuation along the path. So unless you have some ancillary data or some, for example, using KD from MODIS, or unless you have some biological or some other biological assumption that means that you can't, you cannot solve it. So you're using those, but those potentially have large errors. So these two parameters are not independent. So, and because, yeah, and good stuff. So the question is, can we separate these two? And the answer is yes. There is a technology that allows you to separate these two, and that's the technology used in the SRL LiDAR, and that's the fact that molecular backscattering, some of it is shifted in frequency domain tiny bit. It's called Brillouin Scattering. And the shift is tiny. It's in terms of nanometers. I don't remember, but it's a fraction, a tiny fraction of a nanometer. So while the backscattered light from particle is all exactly at the same frequency as you shine. So this shift in frequency between molecular scattering and the particular backscattering allows you to separate the molecular from the particulate. If you have a detector that can sense this independently of that. So you need to have a very good frequency or wavelength detection in your detector. So again, the molecular signals, in our case, water and ions in it is on the side, particular backscattering coming from here, right at the middle of your channel. There's technology to separate the two, and then you can look, you know what water backscattering should be. And therefore you can use the change in the signal of the water backscattering to tell you about the attenuation along the path in the water. So from this one, you're going to get the KD. And then you apply it to this one, and from this one, you get the backscattering of particle. Because for water, you know the backscattering. So it's ingenious, basically. It allows you solving for the molecular separately from the particulate. Both have the same attenuation. Because I know the molecular, I can get the KD here and therefore apply it to my particulate. So these are independent. So this is an example of many of the Riley, the group from not Riley, Langley. The group from Langley has participated in a whole bunch of NASA missions. Sabre is a campaign that Ivona ran, and then others flying over so we can do this matchup between their technique and what we measure in the water. And you can see that the matchup with MODIS is good in terms of KD. In terms of backscattering, the matchup with in situ is good. And the profile they get from in situ versus the profile of the HSRL is good. So there's validation for this technique. It seems to work well and independently. So the KD is important because, again, a priori, you'd think that with a LiDAR, it's going to be beam attenuation that's going to attenuate. Well, it turns out the moment there's a sufficient field of view, very fast, it's something that's much closer to KD than it is being seen. And they were able to get to depth of 3 optical depth, and using that information in primary productivity model, the vertical distribution allows you to improve on your primary production estimate. So what may we want to see in the future in terms of how do we see LiDAR helping in the future? So there's a variety of type of LiDAR that Mike and myself and others have tried to sell to NASA to tell them, you know, this is the minimum we want, and then how can we do more around it? So what you want is at minimum is something that gives you KD and DET independently, that you know well it's calibration error. So another thing I didn't talk about is they have a way also to from airplane in particular it was used to infer the changes in your source signal, and you can do it with the Raman. The Raman scattering tells you about the source signal, the Raman coming off the water. So that just so you know some other signal that you monitor, inelastic signal to tell you about your beam. Yeah, so the ability to separate this is critical with lower than 3 meter in the vertical. And then so this is before, this is Calliope without the separation of these two. That's the minimum, but better constraint of the calibration error. Currently, Young is the only one producing these products. And some of us, like myself, are uncomfortable with that because we don't understand the signal. You can get the raw data, but I'd like to know how the sausage is made. And currently, we don't have a paper. If you read the paper that you wrote about how you get the signal in the water, you cannot go yourself and write. So we need an open software that tells us exactly how you make the sausage of data from Canada. And hopefully it's going to come soon. Then there's HSRL, which is the technology I just told you about, where you separate molecular from particulate, and then you get these separate. And those will improve your geophysical product and give you, independent of ocean color, information that can be used to constrain ocean color, or together better constrain properties in the water. Chlorophyll fluorescence can give you chlorophyll concentration by looking at fluorescence at night, for example, where you don't have to deal, or information about physiology when you compare day to night. And from that, you can get information about iron stress from quenching, because cells that are iron stressed quench differently from cells that are not. And then if you get 355, now you can separate CDOM from chlorophyll absorption. Because a CDOM will more strongly absorb the 355. And then, so better separation of those. Any questions? Yes. Yeah.
I was wondering when they're doing these comparisons, are you backscatter or something?
So independently at one wavelength with the HSRL, we get backscattering and KD. KD, and now if you're a fluorescent channel, you can get local fluorescence independently. That's a third information. Otherwise, KD can be used to constrain absorption. KD is mostly related to absorption, and with that, you need some model to say how much is that versus how much is fiber. It's something that constrain that, and that's cool. Does that answer? Figure from before, which figure is it? Is it way before or here? Way before? Here? So this is, if you just tell me what, Kelsey's paper. So Kelsey's is all backscattering. All they're comparing is backscattering.
Overrated. So are any of those ITAC products, like are there products from ISAC? ISAC.
Yeah.
ISAC.
So, I think you can, whether there's profiles for the ocean, I don't know, but I know that she's Kelsey's is writing a paper on it and probably wrote already software to get around the profile. What I'm seeing is some preliminary profile with up to 27 resolution. You can choose your resolution and then your uncertainty is so it's astounding. But you don't have the repeat is very slow. So you might have one image every 3 months in the earlier papers. So yeah. Did you find out that one? Oh, so you're going back at the polar night. So he's using backscattering here. He's using backscattering as a predictor of phytoplankton. So that goes to paper by Jason Pratt and others, where they found really correctly calculated backscattering, a linear relation to backscattering and phytoplankton biomass as done with flow cytometry, so a sorting flow cytometry that's taking cells and pushing them. Yeah. Does that answer the question?
Yeah, I was wondering like when they're doing the comparison. Yeah, I mean, with opposite side.
So here you only get you only get MODIS data. So it depends on what how far you are. So he's looking at several rings around it, and he gets. So this is, I think, the ring that's you still get a full cycle, and this is the ring where you don't. So this is closest to polar zone, and here you don't. There's no MODIS data where this is hatched. And the comparison again is in the backscattering. It's not in the chlorophyll. Does this answer? Sure. So we're back to here. Yeah, so this is what we're pushing for, and we still think it's valuable for atmospheric science. So you really want to convince them too to be on board. So this is this is the politic of science that I'm bringing to. But it's really important. But again, an ocean optimized ISO will give us better understanding of polar and other regions where the chronically cloudy regions where we don't have a lot of passive. Major improvement in water column phytoplankton stocks and rates by providing vertical structure. Global representative data for ocean column algorithm development. We actually can use much more backscattering if we get it from and it's of high quality from lidars to then see how well our inversion algorithm work and then improve these allocation work by having more data. New information on physiology, looking at ion stress, if you have the fluorescence, insight to day and night stock change, better atmospheric correction, we talked about it, and also what's the right layer for which things are homogenized in the ocean. What's that mixing layer? So it's a ton of science that one could do, and hopefully you guys are going to be the one that benefit from having such a sensor. But then Mike and I will be long retired. So yeah, so the idea is if you fly them together, ocean color with lidars, and underneath you also have your Argo floats. You can combine the strength of the different approach. Just more of what I said before. And we hope to do it with PACE, but it did not work. And there's this Mescal, which was a LiDAR that CNES has been developing. It's still in the works. It's supposed to be in partnership with NASA. Where it's going, we don't know yet. But hopefully this will fly in the next 5 years, and potentially, if it's in the right place, could be brought with PACE. And if this is, and it's not yet, if this is optimized to do ocean. So this is where, lobbying matters. So you do your science and you think, oh, somebody's going to put a satellite up there for me. No, that's not how it works. People will respond to pressure from the community. If the community is well articulate and says, look, with a minimum extra investment of X, we can get a sensor that can benefit ocean community, constrain carbon by this amount, and really propel us to a much better global science than what we can do now for carbon. But you have to back the numbers, you have to have the community behind it, and you have to keep drilling it. Say, okay, I understand it's important, we know why it's important. That's it. Any questions? Yes.
Just in the last slide, you said the next slide, like actually looking at the models there. Much deeper. It's place for a lot of it, or like how deep.
So you can get to about 40 meters. 40, 50 meters, there's people that done simulations. In clear environments. Obviously the dark, yeah, and you can get a sense of it a little bit in this curtain we looked at before. The curtain from HSRL. Sorry, no, really not passing yet. Here it is. So this is about 30 meters, and this is, still relatively coastal. So it's not the clearest environment, and it's from an aircraft. So,
So in a lot of the areas, maybe
yeah, that's the whole. Yes.
How often do they send this down?
Oh, it's semi-continuous. Well, so you send a pulse and you analyze it. It's speed of light. It's the speed by which you get in signals back. So you can calculate. It's fractions of seconds.
So is it like on a satellite with the meter resolution?
100. So the order of 100 meters. And then the question is how much you average to increase the signal. And how big is your antenna? So the bigger your antenna, the more photons you have. It's all about photons. And the bigger your telescope, so the bigger your telescope, the bigger, the more, and the stronger your laser is. So that's those are the kind of that's the case.
There's a LiDAR page on the web book that drives the version of the so-called the Lidar equation. There you can look and see exactly how the backscatter, volume scattering function at 180 matters, the decontinuation. We haven't talked about that yet, but anyway, all these little things that go into it so that you can say, okay, for my system, I have this backscatter fraction, I have this size of the telescope, I have whatever, and you can figure out how big your signal return will be depending on what it reflects off of in the water and so forth. If you're interested in seeing that.
And so do you have a mirror or something, so you can actually get some spot of it? I heard you were moving the laser.
Now, typically they look at one thing. The adversarial scientists would love to do different patterns. Always. They'd rather not look straight down because they get more patterns to the atmosphere. That's again part of the space that's done. You want the ocean, they want the atmosphere. Thank you.
Okay, a little after 9:30, let's start up at 9:45. The sooner we get done, the sooner I get to go to the doctor.